Hi, and welcome to the Low Level Devil channel. This video will be the start of a new series on developing an OS using the Linux as the kernel. This is completely different than the concept of Linux from scratch, if you're familiar with it, which is a great learning resource for those that are interested in creating a custom GNU Linux OS. This one's going to be focused on development at the low level, of course. Before we move on, a little more about what this video is not. It's not an introduction to Linux or how to build a Linux kernel. There are already plenty of videos and resources out there that you can use if you need that type of information. So I'm going to make some assumptions. First, you know what the Linux kernel is. Maybe you've even built your own kernel from source. And of course you know C and maybe some x86 64 assembly. If you don't know the assembly part, don't worry about it. There's going to be very little of that because the kernel takes care of most of that for us. This video is going to be more focused on how you can use the Linux kernel as the kernel for your own OS, for whatever device or that you want to develop on, but you don't want to reinvent the wheel on the kernel level itself. For this video series, I'm going to be using a virtual machine just because it makes it easier to do the recording, but this can also be done on any hardware device that supports the Linux kernel, like Raspberry Pi or any other device. So let's get started. First, I'll show you what I'm starting with here. If I run the lsblk command on the command prompt here, you'll see we have SDA, that's my hard drive. So what I want to do is add another hard drive that I can use for my OS. So I'm going to shut down my VM here. Alright, so now I'm going to go in and add another hard disk. I'm using Parallels, you might be using VMware or whatever. So I'm going to add a hard disk here. I'll make it 1 GB, really small. That's all we need. Just gonna find a location to save it. I'll call it, let's see, my OS 0.0.0.1. Alright, so now let's go and click OK. So now we have another hard disk on that VM. Let's just boot it back up. Okay, now we're back up. Let me open the console. Right, and now if I run lsblk, we see SDB here. That's the new hard drive. So first let me go into a su prompt here. So I'm going to run cfdisk on dev SDB, and I'm just going to create a new partition, default size, primary. Let's make it bootable. And I'll go ahead and write that. Got to yes and quit. So now if I run lsblk again, you'll see we have this new partition, and I assume you kind of know this stuff already, but just describing as I go along. Now I'm going to make fs ext4 esdb1 to make that a ext4 mount. Format our partition. So now I'm going to mount it, and I'll make a directory my OS, and I'm just going to run mount dev sdb1 my OS. So now if I go into my OS directory, you can see it's empty, just a lost and found. I'll remove that. So now we need to start with some basic directory structures that are needed for Linux. So I'm going to start here by doing make directory, and we're going to want a bin as well as a sbin, etc lib64, and let's see, we'll also need var and a dev proc sys run and tmp, yeah. And that's the basic set of directories you need for the Linux kernel to boot up and be able to use. So let's also make a couple of nodes here. So I'm going to make the dev console. This is a character device 5.1, and another one for dev null here. It's also a character device. Just make those dummy nodes. And of course we're going to need a boot folder. So let's go ahead and go into that. And this is where your kernel is going to live. And we don't have a kernel right now, but actually, you know what we do? Let's look at our OS's boot. This is the one it booted up in. Let's just go ahead and use that kernel for now. You know, you can build your own. I'm just going to copy these. And this one actually uses an initial RAM disk too, so let's copy that init rd file. That's only needed if you use that, then you need to include it, otherwise you won't need it. So now let's make this new drive bootable with grub. We're going to run grub install with a couple of flags here. First we need to call dev sdb, not sdb1, sdb, just the full disk. We need to run skip fs probe and set the boot directory. We'll just make it to this mount myos boot. So that's where it'll install the software. Okay, now grub is installed. If we ls, we see there's a grub folder here. Let's go into it. And there's the files. Well, one thing we're going to need is a grub config, so let's just go ahead and make one. Nice simple one. Alright, first we'll set the default option to 0, set the timeout to 30 seconds, and just create a menu entry here. We'll call it myOS 0.0.0.1. And now we'll need to put our kernel information in here. Let me go back to the console and get the names. And, so we'll copy that name. And actually, let's create a new tab here so I don't have to keep switching. For the boot folder. So this VM Linux is our kernel. So we need to run the command linux /boot and then our kernel name. And now we need to set the root partition that it's going to use, which is going to be our dev sdb1. You can also set the init program for your OS. So you could make it whatever, bin, my init. But by default it's sbin/init. And we're going to use that, so we don't even need to add that. So we just need RO at the end. And since we have a RAM disk, we're going to have to call init rd /boot, and let's copy that RAM disk name. Let's see. And paste it right here. And let's save that file. And that's everything that we need to actually boot this drive. Of course, we don't have any code yet though, so let's go ahead and exit this, and we'll go create a source directory. So cd to mount myOS, and here's all our directory structure. So we'll make a directory source. We need to use sudo first. Go into that directory. Okay, now they cleared that, let me just run code in this directory. You can use Visual Studio Code or any editor you want. I prefer code usually. So let's first start by creating start.s file and an init.c file. So since we're creating a raw program here without using the GNU libc libraries, we need this start.s file. We're going to define the global export here as _start, need to do dot text, and we'll start our start section. And all that this is going to do is just going to call main, and that we're just going to put in our main.c. So int main return 0 for now. So now since we have our own OS and we don't have libc, we're going to have to actually manually make system calls to invoke the kernel. So let's look up the system calls. If we search Linux system call table here, this Chromium one's a good link, and I'm using x86-64. So if we click on this here we have a table of all the system calls that Linux has, and you can see this is system call 1, system call 2, 0 is read. There's some references here for it. For the RAX is where you put the number for the system call, then RDI, and all these other registers. There's where the arguments will go. So let's go in here and just set up an export, and we'll call it _syscall. So this is going to be our code to invoke the system call. So we're first going to move RDI into RAX. That's going to be the first parameter of it. And again, this is x86-64 assembly. You may or may not know it. If you really want to know in detail what all of these things are doing, you know, there's plenty of videos out there. I don't want to make this whole video about explaining how assembly works in a specific architecture. So, but you can see all these registers I'm getting on the right side are straight from that document. This is where we need to store things. The ones on the left are the ones that are the values passed in by C when it invokes this function. So let's see, and the last one here, this is going to be argument 5. And then after that, see all these here, those are all the arguments. The first one is the number, and these are all the actual arguments to the syscall. Now we can just invoke syscall and return. So that's pretty much all the assembly we're going to need to write for this purpose. Now if we go into our C code, let's start here by adding a definition for this function, long underscore syscall. And the first value was the number, the system call number, and then a bunch of arguments, argument 0 all the way through argument 5. So that's just the definition of the function, so we can call it in C. And now let's include, we can actually include syscall here, syscall.h, which is just a define. If we look into here, down here in bits syscall, these are definitions for all the different system calls, so you don't have to type the number for it manually. Here we see syswrite. That's the first one we want to start with to actually write some data to the console. So let's go ahead and start adding some more functions here. First I want to make a simple strlen function. Do long underscore strlen. I'm using underscores here just so the compiler doesn't complain that it thinks that I'm using glibc when I'm not including it. That's actually, it's unsigned long here, so let's see. So count 0, just going to loop while the current variable isn't 0. Just a real simple implementation. So that'll give us the length of a string passed in. do want another function here too. I'm just going to create a really simple delay function. Since we don't have timers implemented or anything yet, let's just create one that's going to loop for a number of ticks and do nothing. And at the very start here, we're going to create a message here, my OS 0.0.0.1 initializing, and then put a return at the end. Now we want to delay, let's see, 1 billion. So I guess this is about a 2-3 megahertz processor, so that should be roughly somewhere around a second, maybe 2 seconds or so. It's just a rough estimate. Yeah, I want to create another function here to call our syscall and make it simpler. We'll call it print string, and it'll just take in a, let's see, a char pointer string, and all we're going to do is invoke syscall here, so we can use that syswrite define, and then let's look again here. Write takes in the file descriptor, the buffer that you want to write, and the count of bytes. Now we can use 1 for the file descriptor because that's actually std out. I believe 0 is standard in, 1 is standard out, and we can put the buffer is going to be just our string, and the number of bytes is going to be just our strlen. Actually, let's cast this too so the compiler doesn't complain. Cast this one too. So here we're going to just use strlen stir. This is where, and then for the rest of these arguments, we can just do 0 because they aren't used. That's it for our print string, so let's go ahead and just print this message here, print string, and we'll do which string, yeah, we'll just use MSG here. So now let's just do a while loop forever. This is basically going to be the eventual event loop of the operating system. For now, we'll just print out some tick messages, and we'll start with another delay. Roughly 1 billion ticks, and we'll print string tick. And that's pretty much it for our first set of code, so let's go ahead and try to build this. We'll just use a simple GCC command to build it here, no makefile or anything. First we want to use the no stdlib, the freestanding, and no pi. If you don't include these parameters, it's going to try to link in a bunch of libraries that you don't use yet. So see, we got some warnings here, but that's, oh, there's an error here too, that I need char pointer. Clear it, and there you go, no warnings. So now you see we got an a.out file here. That's our binary. It's only 9,000 bytes roughly. So let's go ahead and copy this a.out file. We'll go back one directory and put it in our sbin folder as init. So now we have ls mount my OS sort, no, not source. Let's see, sbin init, and there's our binary. So that's what Linux kernel is going to boot up with. So let's go ahead and shut down the virtual machine. Okay, now let's go into our properties here and just go to our boot order. All we really need to do is move this hard disk up to the top. So now that's going to be our boot disk. Start it back up, and here you see my OS 0. Oh, we got some failure here. Let's take a look at this. Looks like I put something wrong in the grub config file. So let me go ahead and start it back up. Okay, so now let's go back into to mount the drive, same as we did before. CD over to the boot directory. Okay, we got the init rd there. Let's look at the grub dot sudo vi grub.cfg, and yeah, it looks like we missed /boot in front of our init rd. So if we don't put that, it doesn't find the file, and that's the only thing that we did. So let's go ahead and just shut it down again. Okay, swap that boot order again. And boot it up. Okay, so just hit enter when this comes up. And here you go, the Linux kernel is booting. Tick, tick. And there we go, myOS 01 initializing, tick, tick, tick. And there you go, there's the first part of your OS that's invoked by the Linux kernel and interacts with the Linux kernel. So let's go ahead and boot this back up. And the main advantage to using Linux kernel is you're not reinventing the wheel when it comes to all these hardware interactions. So we can actually take advantage of the fact that our OS can already read files on the file system and has a defined file structure and all that. So let's start by playing around with some of the other system calls. Alright, let's finish booting up. We'll fast forward a bit and remount the drive, and then we're going to run code in the source directory. Alright, so let's take a look at the syscalls again. Alright, so here we have the open syscall. So this is used to open files on the system, and remember, in Linux everything is a file. So if you want to open something, it's a file. So let's give it a file name. Takes int flags and umode. Let's actually look up this system call, Linux syscall open. And here we'll look at that Linux man page for it. And here's some of the details on it. If you don't know how the open call works, these are the C defines for it. And let's see, and FC and TL, we're going to need that. That's going to just be for one of the defines here. So let me paste that up here. Let's just create a new function. We've got an unsigned long open underscore file. Let's see, and char file name. So we actually we want file name and the flags. We don't need mode because we can pass 0 by default if it's just read only. So we're just going to call syscall open. And let's see, we have the file name as the first parameter, then the flags, and 0 for mode, and 0 for the rest. And we want to return the value from there. Actually, we should also, let's see, that's unsigned long. So let's make syscall unsigned long. That's what it should be. Alright, so that's all we'd need to invoke to open a file in Linux. And let's take read. So now if we want to open the file, we want to read it too. And that takes in the file descriptor, which is returned by open, the char buffer, and the count of bytes to read. So we do unsigned long, and let's see, we'll call it read underscore file. So it's going to first take in the unsigned long file descriptor, the char buffer, and let's see, unsigned long size. So here we're going to return syscall sysread, and we need to pass in fd, the buffer, the size, and 0 for everything else. So let's see. Go ahead and after our initial print message, let's copy this delay. We'll have another delay after it prints the initial message. So we're going to create a char buffer here. Let's make it 255 characters. Just read the first 255 characters of the file. Now we can print the string. See, opening file, and actually, yeah, let's include the file name too. So create a char file name, and we're gonna use src init.c, which is our file right here. So we know that's on the file system, so we can read it. So we'll print that file name and then print a return. And now we're going to want to call our new function. So unsigned long fd equals open file, and we can pass in that file name, and this is what we needed that include for. ord only is the flag we want to pass in. So it's just going to open the file in read-only mode. So now that we've opened the file, we have the file descriptor. Now we can call read file to actually read that file descriptor. And we pass in file descriptor, the buffer, and the size of the buffer. So now that we have read the file into that buffer, we can again call print string, and what we want to print out that file buffer, so we can just use that char buffer that we read the bytes into. And from there we'll just continue on to our tick loop. And let's go ahead and rebuild this. Again, same options as before. You can read more info on what those options do if you're interested as well. And let's do an output file. Actually, no, let's just keep it a.out for now. A bunch of warnings, we can ignore those. We have our a.out file here. Here we go. Yep, it's at 10. Yep, and it's just a little bit bigger than it was before. So let's go ahead and copy that over top of our older init. So now that will be our new OS init application. So let's go ahead and shut down. And again, swap the disks around. And boot it up again. So now we have my OS. Let's see. And here's our initializing. And there's the first bytes of our source file. So there we have it. We can read a file from the file system using the Linux kernel in our custom OS. Now that's a good starting point. So I think for the next video, I'm either going to maybe show a couple more system calls, or maybe we'll start by actually adding in some libraries. Since we're using Linux, we can make use of dynamic libraries like libc, so we don't have to write our own system calls as well. It depends on how much of your OS you want to be yours and not just, GNU utilities. So that's a good start to this series. Thanks for watching, and if you enjoyed this series, learned something from it possibly, please like and subscribe, comment with any questions you have, and thanks for watching.